So in this session, we will have one technique on how to identify whether a series is convergent or divergent. And that's with the use of integrals. So by the end of this session here, we will know how to use the integral to test whether a series is convergent or divergent. So before we begin, let us recall the definition of a series and the definition of the convergence or divergence of a series. So a series, it's just a formal infinite sum. Okay, so um, you have some terms an, and then you just add them. Okay, so you have some terms an, and then you just add them. Okay, and then this formal sum here, it may converge or diverge. Okay, so this guy here, this series converges if the sequence of partial sums is convergent. So we recall the sequence of partial sums, the sk. Sk here, it's just the sum of the first k terms in the series. So we collect all these S sub k's. You start with S1, which is just A sub 1, and then S sub 2, that's A sub 1 plus A sub 2, etc. until S sub k, that's A sub 1 plus A sub 2 until A sub k, and so on and so forth. Okay? So you will get a sequence called the sequence of partial sums. Okay? So this guy here will converge if this sequence here converges. Okay, so you look at Sk as a sequence. You find the limit of Sk. If it has a limit, then the sequence Sk is convergent. That also means that the series sum an from 1 up to plus infinity is convergent. Okay, if this sequence here is divergent, then the series is also divergent. Okay, and then we have the divergence test. Okay, a test for divergence. So in here, we look at the series sum of n from 1 up to plus infinity. And then we consider the terms of the series here. Okay, so you consider a1, a2, until an plus 1, etc. Then you look at the terms and you check the limit of the terms as n approaches infinity. If the limit is not equal to 0, then we are sure that the series is divergent. Okay? So if the terms do not go to 0, then the series is divergent. Okay? And then recall the remark I gave. If the limit of the terms as n approaches infinity is equal to 0, then we cannot conclude anything. The series may converge or may diverge. So you have to use other ways to determine whether the series is convergent or divergent. Okay, so that's what we are going to learn starting this session and then maybe up to 3-4 sessions from now. Okay, so we will try to learn some techniques to determine whether the series is convergent or divergent. Let us start with that. Let us consider a series, n from 1 up to plus infinity, and let's get a function f that is continuous and positive on the interval 1 to plus infinity. And such that the terms an, it's just your function evaluated at n. Okay? So if you look at this, the dots that we see here, these are the terms an. And then the red curve here, that's the function f. And as you can see, the dots, okay, they lie on the graph of your function y equals f of x. So that's what we want. Okay? Continuous, positive. Okay? On the interval 1 plus 2 infinity. And such that an equals f of n. Now, let us look at this. So what we're going to do is we divide the intervals into subintervals. Actually, we divide it such that you have here 1, 2, 3, 4, etc. So you look at the interval 0, comma 1. So this interval here. And then you look at this interval here. Okay? And then this interval here, etc. And then you form these rectangles. Okay? You form these rectangles. So if you do this, notice that if you get the area of these rectangles here, okay? If you get the area of these rectangles here, they will be smaller compared, or the sum or the approximate sum is smaller than the area under the curve y equals f of x. As you can see, there are some spaces on here, in here, in here, and here. Okay? So what will we get in here? The integral from 1 up to n of f of x dx. Okay? So what's the integral from 1 up to n of f of x dx? If this is your 1, etc., this is n. Okay? This is n. The area will cover this part here. Okay? Including those white spaces. So the rectangles, okay, the green shade inside the rectangles plus those white spaces there, okay? So you will have this area here. That's your integral from 1 up to n of f of x dx. And as you can see, this area here, okay, this area here, let me get this part. The area of this rectangle, since this is your A1, correct? That's your A1. The height is A1. This guy here, the width, it's just equal to 1. So the area of the rectangle, the first rectangle here, is actually A1. Now, if you look at the second rectangle here, this guy here, it's your A sub 2. And therefore, the height, this height here, it's A sub 2. And again, the width here, it's equal to 1. So the area for this guy here, it's equal to A2. And you continue the process until AN. At this point here, this is your AN because this is N here. The height for this, it's equal to AN, and the width, this guy here, it's N minus 1. So that the width, it's just equal to 1. So if you get the areas of this rectangle, you sum them, you will get A1 plus A2 plus A3 plus until you have AN. But this is precisely S sub n. Okay? This integral here, you look at this integral here, it started from 1. Which means that the integral will only consider from this point up to this point. Okay? So notice, we subtracted this A1 here. This A1 here. Okay? we will have Sn minus A1. This is equal to A2 plus A3 plus until An. Okay? Meaning, we are only considering this area here. These areas here, or these rectangles here. This rectangle here, this rectangle here, 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 etc. But then again, you are calculating the area here under the curve of y equals f of x from 1 up to n, which means this guy here still includes these white spaces in here. So this definite integral here is greater than s sub n minus a1. Okay? Now, if we let n approach infinity, okay? If we let n approach infinity, what we will get, it's the improper integral from 1 up to infinity of f of x dx. Correct? And suppose that that limit of that definite integral from 1 up to n of f of x dx is equal to L. Suppose it's equal to L. Then what will we get? The sum n starting from 1 up to infinity. Okay? This is just the limit of your S sub n. It's just the limit of S sub n here. But because of this relationship here, it will be less than a sub 1. You bring it to the left-hand side there. So the limit of Sn, as n approaches infinity, will be less than a1 plus the limit of the definite integral from 1 up to n of f of x dx. And as you can see, because of this assumption, this guy here, it's just L. It's just a number. And what are we saying here? This sum here is less than some number, which is A1 plus L. Take note that your ANs here, they are assumed to be positive. So if you add positive numbers, all of these guys here, actually the sum, will be greater than or equal to 0. In fact, it's greater than 0. But what's the point? This guy here, it's some positive number. Okay? And it is less than some real number here, which means you will get a sum. This guy here has a sum. It's just between 0 and this number here. It will not go to plus infinity. Okay? So far, so good. Okay, so that's the first part. Let us go back to this. We now have this, etc. In here, we consider this rectangle. Okay? This rectangle here, etc. This time, let us consider a different rectangle, a different set of rectangles. This time, we will have this rectangle here, etc. And look at this. This is still your A sub 1. This is still your A sub 2. This is still your A sub 3, etc. The height of this rectangle is still A sub 1. Here you start from 1 and end to 2. So the length here, it's just 1. And then you have 2 to the 3. So 2 to 3. The length here, it's just 1. The height here, it's just A2. So if you added the areas of these rectangles, you'll just have A1 plus A2 plus until plus AN. If this is, say, etc., say this is your A, this is your N minus 1, this is your N, and maybe this is your N plus 1, etc. Okay? And then same process as before, we'll find the integral from 1 up to N of f of x dx. Okay? From 1 up to N of f of x dx. But this time, the integral from 1 up to N of f of x dx, it will be less than S sub N minus N. Correct? Again, this is 1, this is 2, this is your N. So this is your A sub N here. Okay? So in here, you will have, you want to integrate from this up to this. Okay? But the height of this rectangle here, this is the rectangle. Take note of that. At this end here, you have this rectangle here. Okay? And the height of this rectangle, it is A sub N minus 1. So the sum of these rectangles here, this, and up until this, you will have A sub 1 plus A sub 2 plus etc. plus until A sub N minus 1. Correct? But this guy here, this is just Sn minus A sub N. Okay? So far so good. And you see why this guy here is less than this number here? Because as you can see, the rectangles, it contains this area here, here, and it's beyond the curve. It's above your curve. It should not be, or they should not be, included in your definite integral. So the sum of the areas of the rectangles will be greater than your definite integral. Okay? Now, suppose this guy here, okay, this guy here is plus infinity. Suppose the improper integral 1 up to plus infinity of f of x dx, this is plus infinity. What does this mean? So this guy, it's just the limit. Okay, this is just the limit of the integral from 1 up to n of f of x dx as n approaches plus infinity. And suppose this is equal to plus infinity. If we take the limit as n approaches infinity here, this will go to plus infinity, and it is even less than this number, which means that this guy here will also go to plus infinity. Okay? So the sum an as n runs from 1 up to plus infinity. By definition, it's the limit of Sn as n approaches infinity. This is greater than the limit of f of x dx from 1, the limit of the integral of f of x dx from 1 up to n plus a sub n in here. Okay? And that's going to plus infinity. Which means this guy here, it's greater than your infinity, or this sum here goes to plus infinity, the series diverges. Okay? So that's how we're going to use improper integral. Okay? So on the first part, suppose the limit. Okay, let us see. So on the first part here, suppose the limit is equal to L. Suppose there is a limit. It means that the series will also have a sum. Okay? So in here, if this means that if the improper integral converges, the sum also converges. This guy here, it says that if the improper integral diverges, then the sum also diverges. Okay? Questions? So let us have the theorem here. It's called the integral test. It's called the integral test. Let an be a series with non-negative terms. Take note of this, non-negative terms. We want them to be above the x-axis. We want our terms to be non-negative. Suppose f is continuous, positive, and decreasing. Okay? And such that, and decreasing on this interval, 1, comma, plus infinity. And such that your f of n, it's equal to a sub n for all n. Okay? Then, the series converges if the improper integral converges. So we compute for the improper integral. If it is convergent, we can conclude that the series is also convergent. If the series diverges, if the improper integral also diverges. Okay? So we compute for the improper integral. If it diverges, then the series also diverges. Okay? So again, our series must have non-negative terms. We have a function that is continuous, positive, decreasing on the interval 1 to plus infinity. And here we also have f of n equals a sub n. The evaluation of the function at n, it's equal to the nth term of the series. Then, the series converges if the improper integral converges. The series diverges if the improper integral diverges. Okay? Now, take note. I'll put it here. Remark. What if your function is just decreasing on, say, k up to plus infinity? Here, k any natural number. Okay? K any natural number. Then, you can just use the improper integral starting from k. You can calculate the improper integral whose lower limit of integration is k. It's totally fine. You will get the same conclusion. Okay? This guy here continuous. This guy here converges. Then the series AN also converges. And I am not putting the starting point here of AN. It doesn't matter because we had a theorem from the last discussion. Whatever the starting point, they will have the same conclusion. They will both converge or they will both diverge. Okay? And of course, if this guy here diverges, if this guy here diverges, then the series also diverges. Also diverges. So that's the integral tests. Okay? Now, another remark, if you calculate the improper integral and it is convergent, of course you will find the value for the improper integral. Okay? Now, that value is not the actual sum of the series. Okay? Whatever value you get after calculating the improper integral, it is not the actual sum. Okay? Because as you can see in here, this guy, the actual sum, it's strictly greater than this Sn. Correct? So the actual the improper integral here, okay, it will have this value. Okay, it will have this value even if you added a. This value here is strictly greater than the actual sum. Okay? So the integral test only gives the conclusion whether the series is convergent or divergent. Okay? Questions? Let us consider this example here. Show by the integral test that the harmonic series is divergent. Well, we've shown that this is actually divergent by a different method. But for this, let's just show. Okay? Consider f of x equals 1 over x on the interval 1 up to plus infinity. Then f is continuous on 1 up to plus infinity. Okay? F of x is greater than 0 for all x greater than or equal to 1. Okay? And then what else? F prime of x. F prime of x, this is equal to 1 over x squared. It's negative 1 over x squared. And this is less than 0. Less than 0 for all x greater than or equal to 1. And so f is decreasing on the interval 1 up to plus infinity. So at this part, I used first derivative test. Remember, if the first derivative is negative on an interval, then the function is decreasing on that interval. Okay? Also, f of n, this is equal to 1 over n. So we checked everything. F is continuous. We didn't check this one, but you know, this function, it's discontinuous only at x equals 0. So we can accept this. I can accept this. F is continuous on 1 comma plus infinity. And of course, for all x greater than or equal to 1, 1 over x, it's also positive, or they are positive. And then for the decreasing part, I use first derivative test. And then finally, the evaluation at n. So also f of n equals 1 over n for all n in the set of natural number. So integral test is applicable. Integral test is applicable. Okay? The integral from 1 up to plus infinity of 1 over x dx, this is equal to the limit t approaches plus infinity, integral from 1 up to t of dx over x. But this is just the limit as n approach as t approaches plus infinity of ln of absolute value of x evaluated from 1 up to t, limit as t approaches plus infinity of ln of absolute value of t minus ln of 1. Ln of 1 it's 0, so I will not include it here. I will not write it. But as t approaches plus infinity, this is equal to plus infinity. So the improper integral from 1 up to plus infinity of dx over x is divergent, and therefore the series 1 over n and from 1 up to plus infinity is also divergent. Okay? So that's how we use the integral test to show that this harmonic series from one harmonic series 1 over n and from 1 up to plus infinity is divergent. Okay? Next. Determine if the series 1 over n times ln of n squared converges or diverges. So for this, we let f of x to be the function x ln x squared, okay? Sorry, f of x equals 1 over x ln x squared. And in here, we start from 2, okay? Okay? Because, well, if x equals 1, ln of 1 is 0, so you will have denominator 0. So you should start from 2. So take note of that. Okay? So f, now, f is only discontinuous at x equals 0 and x equals 1. So f is continuous on the interval 2 to plus infinity. Okay? Also, for all x greater than or equal to 2, x times ln of x squared, this is greater than 0. And so, f of x, this is greater than 0 for all x greater than or equal to 2. Okay? Next, we get f prime of x. Okay? F prime of x, what is this f prime of x? Um, let's see. Let us write that as x ln of x squared raised to negative 1. And we want to get the derivative of this. So this is equal to what? This is equal to negative x times ln of x squared raised to negative 2 times, by chain rule, multiply left derivative of right, x derivative of right, it's 2 ln of x times 1 over x plus right derivative of left, ln of x quantity squared. Okay? And let's just rewrite this. This guy here, it's just negative 2 ln of x plus ln of x quantity squared all over x ln of x squared, everything squared in here. And ln of x, it's greater than 0 for x greater than or equal to 2. And of course, these two guys here are being squared, but we have a negative here. This will be less than 0 for all x greater than or equal to 2. So f is decreasing on the interval 2 to plus infinity. Okay? So we have checked continuity, um, decreasing, and positivity. And obviously, we chose this function f of x equals 1 over x ln of x squared because when we evaluate that function at every natural number, we'll just replace the x with the n, and you will have the terms. Okay? For every n in the set of natural numbers, f of n, this is equal to 1 over n ln of n squared. So the integral test applies. Integral test applies. So integral, we start from 2 because that's the, so it means in here, by the way, we start from 2. So in here, set of natural numbers except 1. Because I started from 2. We have here dx over x ln of x squared. This is equal to the limit t approaches plus infinity 1 to t dx x ln of x quantity squared. And here we can just use substitution. U equals ln of x, du equals 1 over x dx. X equals t implies u equals ln of t. Why did I write 1 in here? Again, this is 2. And then x equals 2 implies u equals ln of 2. And of course, as t approaches plus infinity, ln of t still approaches plus infinity. Okay? Which means in here, you can just have your t approaches plus infinity integral from ln of 2 to ln of t. And we will have here du over u squared. And then du over u squared, if you integrate that, what will you get? This is just negative 1 over u. And here we evaluate from ln of 2 up to ln of t. And that's equal to, what is this? So you have limit t approaches plus infinity of negative 1 over ln of t plus 1 over ln of 2. But this, as t approaches plus infinity, look at this. As t approaches plus infinity, ln of t goes to infinity also. So this guy here, it will go to 0. Which means that this is 1 over ln of 2. Thus, the improper integral from 2 to plus infinity of dx over x times ln of x squared is convergent, and therefore the series is also convergent. So series from 2 to plus infinity, 1 over n ln of n squared is also convergent. Okay? Theorem. The series sum 1 over n to the p, and from 1 up to plus infinity, which is called here a p series, okay, is convergent if p is greater than 1, and it is divergent if p is less than 1, less than or equal to 1. Okay? So this is a special series. It's called a p series. So notice, you have 1 over n to the power p. Okay? 1 over n to the power p. So in here, example, the series 1 over n squared, and from 1 up to plus infinity, this is convergent. Is convergent since p is equal to 2, which is greater than 1. And we have seen the harmonic series, and from 1 up to plus infinity, 1 over n. This is divergent since p is equal to 1. And even if you have, say, series n from 1 up to plus infinity of 1 over n raised to 1.00000001, if you have this, right? Since the exponent is still greater than 1, this is convergent. Okay? Since p, which is equal to 1.00000001, this is greater than 1. Okay? For the proof of this, recall when we discuss improper integrals, we solve this guy here. Okay? We solve this guy here. So recall, so not really a proof, so I'll just remove this proof here. Recall, I ask you to integrate. Actually, we calculated this, x to the p, okay? This guy here, it's convergent. So is convergent for p greater than 1 and divergent for p less than or equal to 1. So all you need to do for this p series here, you can use this function 1 over x to the p, and all the conditions are satisfied. And then you do this improper integral, which we actually did, and we have this conclusion here. So it follows. So this guy here follows from this. Okay? So in here, the series sum 1 over n squared is a p series with p equals 2, and hence it's convergent. This series here, the sum 1 over square root of n, and from 1 up to plus infinity, this is also a p series with p equals 1/2. And it is less than 1. So the series is divergent. P equals 1/2 because, again, 1 over square root of n, this is just 1 over n raised to 1/2. Square root of n is n raised to 1/2. So your p is equal to 1/2. Okay? let's have some more practice on the integral test. Determine whether the series, this guy here, is convergent or divergent. So for this, you see, n starts from 2. So e raised to 1 over n, okay? E raised to 1 over n squared. And we start from 2. So we consider f of x equals e raised to 1 over x squared for x greater than or equal to 2. Okay? And then note that um, the function is only discontinuous at x equals 0. So f is continuous on the interval 2 to plus infinity for any x greater than or equal to 2. F of x is positive since exponential is positive and you are squaring. Anyway, you have a positive number being squared. Okay? For the decreasing part, we use the derivative test. Now, let's just write it here. F prime of x. So, quotient rule. You have low. Derivative of high, it's e to the 1 over x times by chain rule, derivative of 1 over x. That's negative 1 over x squared. So that's low derivative of high minus high, e raised to 1 over x times derivative of low, which is 2x over low squared. So this becomes x to the 4. And notice this guy here cancels this. So we will have, don't forget the negative there, so negative e raised to 1 over x minus e, or minus 2x e raised to 1 over x divided by x to the 4. And again, this is what? This is less than 0 because your numerator, they are negative. The denominator, it's positive because you are raising it to 4. And anyway, you have only x there, okay? And you are evaluating positive numbers only. So this is negative for all x greater than or equal to 2. So f is decreasing. F is decreasing on the interval 2 to plus infinity. Finally, we have f of n. This is e raised to 1 over n squared for n set of natural numbers except 1. In fact, even if we include 1, we can still have that, but we don't care about that term. But anyway, so we'll just start from 2. So integral test applies. So we integrate. We integrate from 2 up to plus infinity e to the 1 over x squared dx. But this is just the limit as t approaches plus infinity from 2 to t of e raised to 1 over x squared dx. And in here, we can let u be equal to 1 over x du. This is negative dx over x squared. And then you have x equals t implies u equals 1 over t. X equals 2 implies u equals 1/2. And then what else? As t approaches infinity, u will approach 0. Correct? U will approach 0. But we will use this later. So in here, now we have the limit as t approaches plus infinity, integral from 1/2 up to 1 over t of e raised to, or you have negative e raised to u du. Okay? So evaluating the definite integral, we'll just have the limit as t approaches plus infinity of negative e to the u evaluated from 1/2 up to 1 over t. Okay? And then what is this? We will have the limit t approaches plus infinity. I think I will need more space, so I'll put it down there. Okay. So let me put the continuation on the next page. So equals dot dot dot. So we will have here dot 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 limit as t approaches plus infinity of negative e raised to 1 over t plus e raised to 1/2. Okay? And again, as t approaches plus infinity, 1 over t will go to 0. So this guy here, this is just negative e to the 0 plus e to the 1/2. Okay? And this is just what? This is just a number. E to the 1/2 minus 1. So, the improper integral from 2 to plus infinity dx, so it's e to the dx or e to the 1 over x dx divided by x squared. This one is convergent. Therefore, the series is convergent. The series n equals 2 up to plus infinity e to the 1 over n squared. This guy here is convergent. Okay? Next problem. Determine whether the series arctan over 1 plus n squared and from 1 up to plus infinity is convergent or divergent. Okay? So, for here, we let f of x be equal to arctan of x divided by 1 plus x squared. And then we start from x. So in here, x is greater than or equal to 1. So for this, then f is actually continuous everywhere. So let's just write f is continuous on the interval 1 to plus infinity. Okay. For x greater than or equal to 1, arctan is positive. Okay. So remember the graph of arctan. So I'll just sketch the graph of arctan in here. It's asymptotic to this, y equals pi over 2, and arctan on the positive side of x is something like this. The negative side, it's down here, and it approaches y equals negative pi over 2. So this is positive. All in all, the function is positive. F of x is greater than 0. Actually, greater than 0. Okay? And then, decreasing. Now, f prime of x. So you have low 1 plus x squared. Derivative of high, so derivative of arctan, it's 1 over 1 plus x squared. Correct? The derivative of arctan. Minus high, which is arctan of x. And then derivative of low, so it's just 2x. All over 1 plus x squared, quantity squared. So in here, we have 1 minus 2x arctan of x all over 1 plus x squared, quantity squared. This is our f prime. Okay? Now, at x equals 1, arctan of x, this is equal to pi over 4. Correct? So, 1 minus 2 times 1 times pi over 4. This is equal to 1 minus pi over 2. And pi over 2, it's approximately 3.1415 over 2. Pi over 2, it's greater than 1. Okay? Pi over 2, it's greater than 1. So this is less than 0. So at least we know at x equals 1, the numerator is negative. Okay? Now, this guy here, it's fixed as 1. This guy here, as you increase x, the value of this also increases only. Because again, your arctan here, it's increasing only. And of course, your x, it's also increasing. So in here, for any x greater than or equal to 1, 1 minus 2x arctan of x, this is less than 0. So f of x is decreasing on the interval 1 up to plus infinity. Okay? Questions? So integral test applies. Well, finally, you have your evaluation. F of n, this is just arctan of n over 1 plus n squared. For n, for any n inside the set of natural numbers. So integral test applies, and therefore we can do the improper integrals. We have the integral from 1 up to plus infinity of arctan of x over 1 plus x squared dx. Again, this is just the limit as t approaches plus infinity from 1 up to t. You have here arctan of x divided by 1 plus x squared dx. And again, use substitution. You can just let u be equal to arctan of x. Du will be 1 over x squared dx. Okay? So in here, u equals arctan of x, du equals dx over 1 plus x squared. So if we do this is just the limit t approaches plus infinity, integral from arctan of 1, that's pi over 4, and then up here it's just arctan of t. And then this is just u du. So this guy here, it's just the limit as t approaches plus infinity, u squared evaluated from pi over 4 until arctan of t. And then, again, we continue on the next page. So this is equal to the limit t approaches plus infinity, arctan of t quantity squared minus pi over 4 quantity squared.
So shouldn't it be divided by 2 since it was u and then
Correct,
it becomes u
correct.
squared
You
over
are
2?
correct. Thank you. So there's an over 2 in here. Thank you. So you have over 2 for this. And then, like I said, in this drawing here, as t approaches plus infinity, the graph of the arctan just approach pi over 2. Okay? Which means this is just pi over 2 quantity squared minus pi over 4 quantity squared all over 2. So you can write the final answer like this if I ask you to evaluate certain improper integral. But the point in here is that, so the improper integral from 1 up to infinity of arctan of x over 1 plus x squared dx is convergent. Therefore, the series is convergent. For the series arctan of n over 1 plus n squared, and from 1 up to plus infinity is also convergent. Okay. Any questions? Next here, determine whether the series is convergent or divergent. Series n squared e raised to negative n cubed, okay, and starting from 1 up to plus infinity. So for this, let f of x be equal to x squared e raised to negative x cubed. Okay? For you, I want you to verify. So this guy, we start from x equals 1. So our x is greater than or equal to 1. Okay? So try to verify all the conditions needed. So verify. One, f is continuous on the interval 1 up to plus infinity. 2, f of x is greater than 0. Okay? For all x greater than or equal to 1. 3, f is decreasing, okay, on some interval here. I think it's decreasing starting from 1, but just try to verify this. So verify from 1 up to plus infinity. That's the interval. And of course, obviously, you just have f of n. This is n squared e raised to negative n cubed. So verify this. Practice on your own. Okay? After verifying all of these four here, integral test applies. Okay? Oops, integral test applies. So if after you verify, conclude that integral test applies. And then we just move on to the improper integration here. So the integral from 1 up to plus infinity of x squared e to the negative x squared, x cubed dx. So by definition again, limit t approaches plus infinity, integral from 1 up to t x squared e raised to negative x cubed dx. Then u equals negative, well, let's just write x cubed. Du equals 3x squared dx. So this guy here will just have the limit as t approaches plus infinity. You have negative. No, there's no negative, but we have 1/3 because of this 3 here. And then we have e to the u, e to the negative u. And then limits of integration will be from 1 up to t cubed. And then you have the du here. So this is equal to the limit as t approaches infinity. You have 1/3 times negative e to the negative u evaluated from 1 up to t cubed. So here we will have now the limit as t approaches plus infinity of negative 1/3 times e raised to negative t cubed minus e to the negative 1. And as t goes to plus infinity, negative t cubed will go to negative infinity. So e to the negative infinity, that's just 0. So this is just 1 over 3e. Okay? And therefore, the improper integral is convergent. So we have here improper integral from 1 up to plus infinity of x squared e raised to negative x cubed dx is convergent. Okay? Thus, the series n squared e raised to n cubed and from 1 up to plus infinity is also convergent. Okay? Okay? Now let us talk about estimating sums. Okay? And for this, we will try to estimate the sums using the improper integral. Okay? So for this, we consider the series and suppose it is a convergent series. We let S to be the sum of that series. We consider the sequence of partial sums for your series. So let Sk be the sequence of partial sums. And here, we define R sub k via this formula. So R sub k is equal to the sum of the series minus S sub k. So it means you have this actual sum. Take note, this sum is A1 plus A2 plus dot 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 plus AK minus 1 plus AK plus AK plus 1 plus AK plus 2 plus dot dot dot. Okay? Therefore, you have your RK, it's equal to the sum, which is this guy here, and you subtract SK, meaning you remove this part here. Okay? So you remove that part. So you will be left only with ak plus 1 plus ak plus 2 plus ak plus 3 plus etc. So we call this rk the remainder, or sometimes the error, when we remove s sub k. Okay? Or when we use s sub k to approximate s. Okay? So rk, it's the remainder or the error made when s sub k is used to approximate. Okay? Sorry about that. Okay. Now, if the series here is convergent and it is equal to S, then for any positive real epsilon, real number epsilon, we can always find some integer k such that the remainder in absolute value is less than epsilon. What does this mean? You choose a very, 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 very small positive number. Okay? You can always find the first, the first, the sum of the first k terms, okay, such that the remainder rk will be less than your chosen epsilon. Meaning, we can always make this r sub k as small as possible and as small as we wanted. And that will mean that your sk will be as close as possible to the actual sum. Okay? So the question is, how can we find that integer k? How can we find that integer k? So to do that, remember, we can use this guy here. Okay? And I said earlier that we can use improper integral. So that's what we're going to do. Okay? So to summarize what I said a while ago, so this means that if we wish to find a partial sum that approximates S up to within some positive number we chose, then we will need to find this positive integer k satisfying this condition here. Okay? Satisfying this condition here. And once we know that, then we can find an approximate value for S. The desired approximate value for S. So to do that, we use this theorem. Suppose f of n equals an, where f is a continuous positive decreasing function for all x greater than or equal to n. Take note of that. Okay? And suppose that your series is convergent. We define r sub k to be the remainder. So you have s minus s sub k, where s is the sum of this series and s sub k is the partial sum. Then your r sub k will just be between this and this two improper integrals here. Okay? So in here, we will be able to approximate where the remainder is. Okay? And using these integrals in here, we will be able to find what the value of k is. And once we know that value of k, then we can add the first k terms. That's a good approximate value for s if we require the error to be as small as possible, or the error to be between these two guys here. Notice, by adding s sub k in the inequalities, we have the following. In the middle, if you add s sub k, you'll just get the sum. It's this guy here. On the left and right hand side of the inequalities here, well, you just add that. Okay? But at least we know where our s will be. It's just between this number here and this number here. Okay? Let us try this theorem, and let us try the methods in here. Look, approximate the sum of the series 1 over n cubed by using the sum of the first 10 terms. Find the error involved in this approximation. And then, how many terms are required to ensure that the sum is accurate to within 0.0005? Okay, to within this number here. And then, using the results above, give an interval containing the value of this guy here. Take note, this guy here, this is a P series with P equals 3. And P is greater than 1. This is a divergent series. Okay? So, let's start with 1. Let's have 1. So, in here, we just want, we just want the first 10 terms. So, we have S sub 10. Okay? Sum of the first 10 terms. So, you have 1 plus 2 cube plus, 1 plus 1 over 2 cube plus 1 over 3 cube. Then you continue this until plus 1 over 10 cube. Okay? And let us use some calculator in here. So try to use your calculator. Okay? And then we'll see. The sum that I got here, it's, well, this is just an approximate value. So approximately 1.1975319. I'll stop at here. Okay? So this is the sum, S sub 10. Estimate the error involved in this approximation. If we go back to this theorem, the error, you look at this, the error, it's just between this and this guy here. Okay? So the error is just between this and this guy here. So let us estimate that error. It means that your error R sub 10, this is greater than or equal to the integral from 11 up to plus infinity of 1 over n, 1 over x cubed dx. But R sub 10 is less than or equal to the improper integral from 10 up to plus infinity of dx over x cubed. So if we evaluate this, okay, you do the limit thing, you do the limit process here, as well as in this part here, you will end up with the limit as 10 approaches plus infinity of negative 1 over 2, 1 over x squared, evaluated from 11 up to plus infinity. So this is, up to t. This will be less than or equal to r sub 10 and less than or equal to similar limit as s approaches plus infinity, okay, of negative 1 over 2, 1 over x squared, evaluated from 10 up to s. And this will give us what? Rk, or r sub 10, will be greater than 1 over 2 times 11 squared, 121, but less than 1 over 200. So in here you have 242. 242. So your error must be between these two guys here. If you use our calculator, 1 divided by 242, this is approximately 0.0041322, etc., less than or equal to R10, less than or equal to 0.005. Okay? So your R10 must be between these two numbers. This number here and this number here. Okay? So this is for number 1. For number 2, how many terms are required to ensure that the sum is accurate to within 0.0005? Okay? So we want our error, r sub k. So how many terms are required? We want to find k. We want r sub k in absolute values to be within 0.0005. Okay? To make sure that this will be true, okay? To make sure that this inequality be true, we will find the k, find k integer, positive integer, okay, such that the integral from k up to plus infinity of dx over x cubed is less than 0.0005. So we want to find the k such that this is true. It will follow that this guy here will be less than 0.0005. Why is that? Again, look at this theorem. Your r sub k, it's less than this guy here. So if this guy is less than 0.0005, then this guy will be less than this. So we just need to make sure that this is true for the k that we will solve. But then again, what is this? Now, integral from k up to plus infinity of dx over x cubed. Again, this is the limit as t approaches plus infinity of integral from k up to plus infinity of dx over x cubed. This is equal to the limit t approaches plus infinity of negative 1 over 2 x squared. Correct? Evaluated from, sorry, why infinity on this part? It should be t already. Evaluated from k up to t. And just write the step in here. You will get finally 1 over 2 k squared. Okay? So you want this guy here to be less than 0.0005. Okay? Following? So, let's solve for k. This implies that 1 over 2 times 0.0005, this must be less than k squared. Or your k squared must be greater than, so this must be greater than 1 over 0.001. Correct? 2 times 0.0005, that's 0.0001. 1 over 0.001, what is this? This is just 1,000. Correct? So you need your k squared to be greater than 1,000. So this means that your k must be greater than square root of 1,000. But this is square root of 1,000, it's 10 square root of 10. Okay? And what is this 10 square root of 10? It's approximately 31.623. So you want your k to be greater than 31.623. So you choose k equals 32. You may choose k equals 32. Okay? Okay? So this means we can take k equals 32. This means that this means that the error r sub 32 will be less than 0.0005. So how many terms? 32 terms. Okay? Questions? For number 3, using the results above, give an interval containing the sum 1 over n cubed. So let's choose k equals 32. Let's choose the result in item number 2. Because if we choose item number 2, the error is smaller compared to just choosing 10 terms. So at least we will have a smaller interval that will contain S. So we are going to do this part here. Okay, we are going to do this part here. So from here, so for number 3, we let k equals 32. So let us use this. Just try to write the details for this. You have this guy here. The integral from k up to infinity of dx over x cubed, we have seen this to be 1 over 2k squared. So just write the details. This is 1 over 2k squared. Which means that if I replace k by k plus 1, I just again have this guy here, but instead k plus 1 there. Okay? So this means your S, the actual sum, the sum 1 over n cubed, and from 1 up to plus infinity, this will be greater than S sub 32 plus 1 over 2 times 33 squared, but it will be less than, actually there could be an equality according to this guy here. So let's put the equality also. And then in here will be less than or equal to S sub 32 plus 1 over 2 times 32 squared. Let's have S sub 32. This is the sum from n equals 1 up to 32 of 1 over n cubed. Let me give this part. Right? So sum from 1 up to 32. So this guy here, it's approximately 1.02, sorry, 1.201, 201, 5836, 5836. And there's more. But anyway, I'll just use this. This is S sub 32. And then let's have 1 over 2 times 32 squared. So 1 times, let's start with 33 squared. So I have 1 over 2 times 33 squared. This is approximately equal to 0.000454591. And 1 over 2 times 32 squared, this is equal to, so if you are wondering how I am getting these numbers, I'm using calculator. Okay, I am using my calculator here, so don't worry about that. 0.0004882 blah blah. Okay, so for the left hand side, for this guy here, we'll just have to add this and this. Okay, I'm gonna add them. 1.201 5836 plus 0.0004591. So in here, on the left hand side, I have 1.2, so 1.2020427. So it says that this sum here will be greater than or equal to this guy here. And from 1 up to plus infinity, 1 over n cubed. But it is less than or equal to, I have here 1.2020718. Okay, so this guy here, it's between this number and this number. So that's an interval for the sum, 1 over n cubed. By the way, if you look at this, you see this, okay? It's 0. It's 0.0004. Here, it's also 0.0004. So it's within this guy here, correct? So our calculations are just fine. Okay? Now let me just write the actual sum. Well, not really the actual sum, but at least a more decimal places. So the sum from 1 over, well, the sum 1 over n cubed from 1 up to plus infinity. Let's write this. Okay. This guy here, it's approximately equal to, let us see. It says 1.2020569. And is it within? Yes, look. 20205. That's the middle part. In here, you have 20204. So this guy, it's greater than this. And then here you have 20207. So indeed, this guy here, it's within this and this. Okay.